welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the figures that count in the history of mathematics. I'm Benjamin Cornish, and today we meet someone who didn't just love numbers, he wrote sonnets about them. Literally. Nicomachus of Gerasa was a mathematician, a philosopher, musician, mystic, and possibly the ancient equivalent of that one friend who turns everything into a monologue about numerology. Gerasa, modern-day Jerash in Jordan, was part of the Roman Empire when Nicomachus lived, somewhere around the 1st century CE. We don't know a lot about his personal life, but we do know he was heavily influenced by Pythagorean thought. The Pythagoreans believed that reality itself was numerical, and Nicomachus really ran with that idea. If Pythagoras planted the seed, Nicomachus wrote the gardening manual. I used to have a friend I met online. We got on like a house on fire. We chatted for years on Foria about the pluralization of Latin words. One day, we decided to meet up for the first time, as we just so happened to live in the same village. We met down by one of the nearby aquaria, and, well, it was very awkward. It turns out that most of the basis of our friendship was a false representation of our in-person characteristics. His real name wasn't even Catfish 3000, and I'm ashamed to admit I'm not quite as charismatic in person as I am when presenting top-class history of maths podcasts. We never spoke in person again after that, but continue to fill the forum pages anytime a city opens up 2 stadia, as we lecture all from our respective podia. So here's the question. Is our friendship real if it's exclusively online? Do you have any friends that have already passed the Turing test? And have you ever asked yourself what is real? Is the world of the mind the only place you can be actually certain exists? The one where you are the only sentient being, thinking and therefore existing, and, as a result, is it the case that the things that we think we experience, material objects like the feel of your headphones, the sound of a top-class maths history podcast, the taste of joy as you award it 5 stars, and the warmth you feel as you share it with your friends and family on social media, is that not real? Or, alternatively, is the mind an emergent property of the materials that construct it? Do atoms exist? And in a certain arrangement of those atoms, where you get a silicon crystal, and if you arrange enough silicon crystals in the correct way, they can form a computer chip, which, if the electromagnetic rays hit the chip at the right frequency, it causes the speaker to reverberate, which pushes other atoms in such a way towards your ears that it gives the illusion of a perfectly enjoyable top-class maths history podcast. When you give this episode 5 stars, does that only actually affect a couple of tiny capacitors in a central stack of computer chips? Or does it change the relational properties of the being that is you in the world of other maths history enthusiasts? What is real? This debate is a bit of a hatchet job explanation of the dichotomic views of idealists and materialists. The idealists believe that constructions of the mind are the true sense of reality and everything else is subject to doubt, and the materialists believe that only the physical structures of matter is real and all ideas are just emergent properties of that matter, like the universe dreaming of itself. If you consider yourself to be a materialist, great news, you're on the same team as Karl Marx. And if you're an idealist, then you can team up with Immanuel Kant, or to put it in terms of a history of maths, are you Team Plato or Team Democritus? Okay, well, now we have caused plenty of schism in the nature of reality. Now you may ask the question, where do numbers fit into reality? Does the number 5 exist in and of itself? Or is it only called into existence when we have 5 of something, like 5 stars given for this podcast? This is where we get into the slightly mystical world of the Pythagoreans, who believed, in part, that the existence of number was much more substantial than the existence of mere substance. And in fact, the, quote, real world around us is really just comprised of numbers. I suppose in not a terribly different way to some quantum theorists of today. Nicomachus lived in this world. Nicomachus, like absolutely everyone else so far, was a philosopher in the broad sense, someone concerned with the nature of reality, ethics, and the human soul. This was an era when mathematicians didn't confine themselves to the chalkboard. Numbers were cosmic, They had spiritual meaning, ethical weight, even musical tone. To understand arithmetic was to understand being itself. To hear more about this mysticism, check out the Injectives episode I did with Dr. Daffin. In his day, maths was still mostly a spectator sport. This was before algebraic notation, before symbolic logic, before anyone invented the equal sign to make things even. So maths meant something different. It was closer to metaphysics. More Plato, less Desmos. Nicomachus was a Neopythagorean, which is exactly as mystical as it sounds. These were philosophers who revived and reinterpreted Pythagorean ideas through a Platonic lens. I should note here that they are a completely different school to the Neoplatonists, who were arguably people that tried to revive the works of Plato, but through, well, I suppose a Pythagorean lens. The Neo-Pythagoreans believed that the soul was eternal, that the universe had an underlying harmony, and that numbers weren't just tools, they were truths. So when Nicomachus sat down to write about arithmetic, he didn't do it with the dry detachment of modern textbook authors. He wrote The Introduction to Arithmetic, a bestseller by ancient standards, with the passion of someone composing a love letter to the integers. Now let's talk maths. Nicomachus's most important work, The Introduction to Arithmetic, was written in Greek, though we mostly have Latin translations today. It was one of the earliest works intended not for other professional mathematicians, but for students, possibly even teenagers. So yes, if you're a high school and you hate your maths textbook, just be grateful it's not from the 1st century CE. Of course, we say here one of because it's believed that Euclid's Elements was also intended as an introductory textbook, although it is far from accessible to students. I myself have the letters M Math after my name, and I still struggle to read Euclid. What makes the introduction so significant is its role in shaping how arithmetic was taught for over 1,000 years, until the 12th century. This was the go-to guide for understanding numbers. It was for number what Euclid was for construction. The book is structured into 2 parts, one on numbers themselves, which he calls the absolutes, and one on numbers in relation to others, the relative. In other words, what is a number, and how it behaves at parties. So let's break down some of the key content. Nicomachus was obsessed with what he called perfect numbers. These are numbers that are equal to the sum of their proper divisors. For example, 6, which is 1 plus 2 plus 3. Another is 28, 1 plus 2 plus 4 plus 7 plus 14. Perfect numbers, the older sibling of other numbers which their father wishes they could be more like. This idea came straight from the Pythagoreans, who saw perfection as a kind of divine attribute. To be perfect wasn't just to be mathematically balanced, it meant you were ethically and cosmically aligned, a sort of numerical enlightenment. He also discussed amicable numbers, like pairs of 220 and 284, where each number is the sum of the other's proper divisors. These were considered signs of friendship, because nothing says BFFs like mutual divisor appreciation. In a world without variables or symbolic notation, categorizing numbers was a way to understand the nature of reality. Nicomachus gave detailed classification, odd and even, prime and composite, square and triangular, and more esoteric types like superabundant or deficient. Yes, some numbers were seen as incomplete, which frankly sounds like something you'd hear in a therapy session. But behind these metaphysical musings was real mathematical structure. His definitions were rigorous. Even his motivations were a bit, well, let's say, numerologically poetic. Pause to wait for the listener to shout at their device. Oh, go on then. Let's do superabundant and deficient. For this, we need to introduce the divisor function, often denoted with a delta. So delta n is the sum of all the divisors of n, including n itself. So delta 2 is 2 plus 1, which is 3. Delta 4 is 1 plus 2 plus 4, which is 7. A number is deficient if delta n is less than 2n. Or you could look at the proper divisors, which is the Aliquot sum, which is less than n itself. So 4 is deficient because 1 plus 2 plus 4 is less than 2 times 4. In converse, a number is considered abundant if the Aliquot sum is greater than n. So 12 is the first abundant number because 1 plus 2 plus 3 plus 4 plus 6 plus 12 is greater than 2 times 12. So 28 is greater than 24. Here, I may indulge myself by reading a translation of Nicomachus. Among simple even numbers, some are superabundant, others are deficient. These two classes are as two extremes opposed to one another. As for those that occupy the middle position between the two, they are said to be perfect, and those which are said to be opposite to each other, the superabundant and the deficient, are divided in their condition, which is inequality, into the too much and the too little. But hang on here, we just define numbers to be abundant, but this translation says superabundant, and that's because in modern number theory we define it ever so slightly differently. So for a number to be superabundant, we are looking at the ratio of delta n and n, specifically set as a fraction delta n over n. So again, for 4 this would be 1.75, or 7 divided by 4. We then compare this ratio to every natural number less than n, and if the ratio for n is greater than all previous, we call it superabundant. So 4 is superabundant because 7 over 4 is greater than 1 over 1, and 3 over 2, and 4 over 3, but 5 is not superabundant because 6 over 5 is smaller than 7 over 4. Gee, wasn't that fun? Why do they not teach abundancy in maths lessons these days? If you thought Nicomachus was content just to categorise integers, think again. He was also an early music theorist, writing a work called Manual of Harmonics, an exploration of the relationship between mathematics and music. The idea goes back to Pythagoras, who supposedly discovered that harmonious musical intervals correspond to simple numerical ratios. For example, the octave corresponds to a 2-to-1 ratio, a fifth is a 3-to-2, a fourth is a 4-to-3. Nicomachus took this very seriously. He believed the entire cosmos was structured around these ratios, the music of the spheres, he called it, not as a metaphor, but a literal cosmic noise made by the movement of the celestial bodies. Modern astronomy would disagree, but to Nicomachus the planets were basically a divine boy band, playing in the vacuum of space where they cannot hear their groupies scream. In his view, learning arithmetic wasn't just about counting change or designing aqueducts, it was about turning your soul to the universe. And honestly, who doesn't want to resonate with Jupiter? His focus on harmonics would go on to influence later thinkers like Boethius, and eventually the musical traditions of the medieval Quadrivium. Hey, it's the friend of the podcast, the Quadrivium, the 4 things that you had to learn on a maths course. Music was one of these 4 essential liberal arts, alongside arithmetic, geometry and astronomy. Actually, my first band was called the Quadrivium. One of the more striking things about Nicomachus's work is what it lacks. Symbols, formulae, and generalizations. There's no algebra in his arithmetic. Everything is given in examples. Want to explain a square number? You show a list of square numbers. Want to explain of cubes? Same deal. Nicomachus didn't abstract, he illustrated. To modern ears, that sounds inefficient, but it made sense in context. Greek mathematics wasn't symbolic, it was rhetorical, expressed in full sentences, not letters and signs. Algebra wouldn't bloom in the West until much later, especially after translations of Arabic mathematicians like al-Khwarizmi and al-Karaji. Still, even without algebra, Nicomachus laid out the properties of numbers in a way that hint at general patterns. He discussed progressions, arithmetic and geometric, and showed their importance in both maths and music. He even calculated the sum of the first n integers, squares, cubes, using example tables. For instance, the formula 1 plus 2 plus 3 plus ... up to n is n times n plus 1 over 2. That was known, but not proven algebraically. Instead, Nicomachus would have shown it for several values of n, noticed the pattern and called it a day. Ancient proof by stubborn repetition. What's interesting is that even in this early non-symbolic form, he had a clear understanding of mathematical regularity. You might remember this particular sequence. Usually it pertains to a story of a young 7-year-old Gauss. Sorry, little Friedrich, Nicomachus got there before you. Oh, I would say got there first, but this is almost certainly not the case. It's just, this is a really old textbook with it written down with someone's name on it. I personally subscribe to the historiological view that the ancient Babylonians knew absolutely everything about everything, they just didn't write it down in a way that survived history. Let's talk data. One of Nicomachus's signature moves was building number tables, systematic ways of observing patterns. For example, Nicomachus tabulated square and cube numbers extensively. He even noticed that the sum of the first n odd numbers is n squared, so that is 1 plus 3 plus 5 plus ... up to 2n take 1 is n squared. Go on, try it. I'll wait. 1 plus 3 plus 5 plus 7 plus 9. Tell me when to stop. Plus 11, plus 13, plus 15. Alright, we got 64. Now, Nicomachus didn't prove this in the way that we do it today, with induction or with algebra. But he'd note the pattern, maybe point to a diagram, and declare its truth. To him, the beauty of the pattern was almost proof enough. He also wrote out long progressions. Geometric sequences, for example, showed up both in his Arithmetic and in his manual of the harmonics. You could say Nicomachus was early to the sequence party. He'd say 1, 2, 4, 8, 16, 32, and link these to musical intervals or cosmological structure. Because when Nicomachus played the numbers, he really jammed. But let's not forget, in an era without symbolic algebra, spreadsheets, or Wolfram Alpha, listing out number properties was the most rigorous way to prove something. It was maths as a mosaic, each entry contributing to a larger, more mystical picture. If Nicomachus had a fan club, its name would be Numbers Are Everything. And if it had a tribute band, it would cover Pythagoras, Plato, and Archytas. His Neopythagoreanism wasn't just a maths hobby, it was a worldview. Pythagoras, of course, had argued that numbers were the underlying reality of the universe. Plato, who came a bit later, took this and ran with it, adding a layer of forms, abstract, perfect ideals of all things. Archytas noticed everything in nature was measurable, like speed, weight, length. And Nicomachus blended these ideas and made them curriculum. He believed that arithmetic came before geometry, music, or astronomy, in the intellectual hierarchy. Why? Because all other disciplines use number in some way. Geometry divides space using number. Music expresses ratio using number. Astronomy tracks cycles and harmonies of heavenly bodies, again using number. So, in Nicomachus's view, to understand arithmetic was to understand the divine architecture of the cosmos. No pressure. Today, we might laugh at the idea that the number 6 is more virtuous than 8. But Nicomachus wasn't joking. To him, number wasn't just a quantity, it was a quality. It had personality, character, even ethics. At this point, I might read to you from one of my private WhatsApp messages. As I've mentioned in the past, I run a maths chat show on YouTube, who, by the way, are sponsoring this show. If you go to YouTube, you can watch it for free. In the group chat, one of the contributors said, "I don't want to be on episode 5. To me, it gives off toxic masculinity vibes. I'll wait for the number 8, which is more dolphin-esque." You may be asking, okay, but who actually read Nicomachus? And the answer, pretty much everyone who mattered for 1,000 years. His Introduction to Arithmetic was translated into Latin by Boethius in the early 6th century. You may remember Boethius from one of our earlier episodes, that is, if you're listening in reverse chronological order. If you're doing it the normal way around, then he's going to be the one who writes the Consolation of Philosophy while waiting to be executed, which is one way to pass the time. Boethius turned Nicomachus's work into the standard arithmetic text of medieval Europe. This made Nicomachus a huge influence on the Quadrivium. Monks, philosophers, and theologians studied Nicomachus alongside scripture. Why? Well, because he connected maths to the divine. His work aligned perfectly with the medieval belief that knowledge of number brought one closer to God. Maths wasn't just true, it was sacred. Even after algebra swept through Europe in the 12th and 13th century, Nicomachus's work stuck around. His style may have aged poorly, no variables, no formulae, but his categories and terminology stayed alive. It's a bit like reading Shakespeare today. Sure, the language is a bit old-fashioned, but the themes still hit hard, and some of the puns are surprisingly decent. So, how does Nicomachus hold up today? On the one hand, we've moved way beyond his methods. Symbolic algebra, calculus, number theory, set theory, none of that appears in his work. He didn't know 0 was a number. He didn't use place value. He thought fractions were less important than whole numbers because they were imperfect. And yet some of his ideas still echo. Take his interest in figurate numbers, squares, triangular numbers, pentagonal numbers. These ideas became part of early number theory. They even influenced Pascal, Fermat, and others who studied patterns and formulae hidden in these shapes. Or his passion for numerical ratios in music. That became the basis for just intonation, a tuning system still used in certain musical contexts. And his musical maths deeply influenced the likes of Kepler, who believed that planetary motion did have harmonic meaning. Even perfect and amicable numbers, once mystical curiosities, are now objects of study in recreational and theoretical mathematics. The search for perfect numbers continues, by which I mean we have only found 52 of them, which is a major increase from when I first learnt this fact back at school. In my research for this part of the script, I've checked the OEIS, the Online Encyclopedia for Integer Sequences, and the most recent update was the 23rd of June 2025, so only 6 weeks ago, which confirmed that 742.07281 is the exponent of the 49th Mersenne prime, thus giving us the 49th known perfect number. But we still have absolutely no idea if it's possible to have an odd perfect number. Never found one, can't prove there won't be one. In fact, every known even perfect number can be written as 2 to the power of p take 1 times 2 to the power of p take 1, where 2 to the power of p take 1 is a Mersenne prime. That formula wasn't Nicomachus's, but he definitely would have appreciated its elegance. If he had emojis, he'd be sending heart eyes to 496. So while his framework has been replaced, the questions he asked are still with us. What makes a number special? What patterns exist in the chaos of counting? And why does maths feel meaningful and not just hard work? Nicomachus reminds us that maths isn't just computation. It's character, beauty, philosophy, dare I say, poetry. We'd be rounding out the picture with only half the story if we didn't talk about where Nicomachus falls short. His works aren't exactly paragons of mathematical rigour. He often asserts truths without demonstration. He's more interested in patterns than proofs. And that's okay, because he wasn't trying to be Euclid. His job wasn't to invent the geometry of the world. It was to persuade you that numbers matter, that arithmetic had meaning beyond practicality. Even so, later scholars found his mystical bent a little much. There's only so long you can wax poetic about perfect numbers before someone asks you to show your work. And Nicomachus didn't care about computation the way we do today. He wasn't interested in finding methods to solve problems. He wanted to understand what numbers are. And that might feel unsatisfying to a modern student, especially one trying to finish a worksheet on factoring quadratics. But for Nicomachus, arithmetic was about contemplation, not application. He thought numbers were eternal, immutable, the closest humans could come to truth, which makes his maths not just a subject, but a way of seeing the world. So here we are, 2,000 years later, still talking about Nicomachus of Gerasa. And while we may have put aside some of his mystical interpretations, no, 7 is not objectively more spiritual than 9, we've inherited his passion for numbers that resonate beyond the page. His work reminds us that maths isn't just abstract logic or test-taking strategy, it's an attempt to find order, harmony and meaning in the universe. Sometimes that takes the form of a quadratic formula, sometimes it's just the thrill of recognising a pattern that feels too perfect to be random. If Pythagoras was the prophet of number, Nicomachus was its poet. He gave language to the emotional side of mathematics. He helped generations of thinkers treat numbers as more than tools, as friends, square friends, rational friends, even complex friends. And that's all for today's episode of the Mathematicians Podcast. If you enjoyed this episode, don't forget to be in harmony with the universe and leave a review and subscribe. You can also follow the pod on Blue Sky at mathematicians-pod for slightly less serious content. And join me next week, where the opera of mathematics continues in a similar melody. We'll explore a world where numbers have personalities and the cosmos hums along to a hidden scale. We'll meet the philosopher who turned all of that into a study guide for reading Plato, and discover why history remembers him as Theon of Smyrna. Until then, goodbye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.